All right. So, this digress, this paper is a very popular paper. Whenever you want to read a paper about diffusion on any discrete data like language or graph, you can consider like this. You can see if they are modeling their space as continuous or discrete, and also if they are modeling the time as continuous or discrete. So there are different possibilities. If we have this, so digress is here. It's the discrete space and discrete time. So this part. And this is a very popular approach. Instead of elbow, they just simply model the cross entropy. So it's very easy to train. And this paper in ICLR 2023, just 2 years ago. But after this, so many papers about graph generation using diffusion. Some people use the continuous time, like the continuous time Markov chain. And this paper introduces digress. And they use graph transformer for their denoising model. And they improve sample quality by introducing Markovian noise model that preserve the marginal distribution of node and edge types during diffusion, and by incorporating auxiliary graph theoretic features and a procedure for conditioning and generation and graph level features is also developed. So it is also the first model to scale to the large guacamole dataset, which has 1.3 million drug-like molecules without the use of molecule-specific representations. So it's a discrete space, discrete time modeling. And so it's a Markovian. So at any, if this is the Q, so at time Z1, Z2, ZT, T minus 1, this transition, this forward transition is Markovian. It only depends on this. Most of the methods, 98% of the methods, papers, use Markovian approach. 2% use non-Markovian. Of course, their elbow is again the same thing, but their sampling is different from their training. Like the novel idea that we go from DDPM for computer vision, that we train with this. For sampling, we use this implicit model, denoising diffusion implicit model. And for sampling, they use this for training. And the elbow of both of them are equivalent, completely the same. But so here is the same. It's a Markovian transition. It's a Markovian process. And the posterior, which is very important, should have this is a requirement if a diffusion model to be efficient. They say that they need 3 requirements. The posterior should have a closed form expression so that X can be used as a target of the neural network. So the posterior distribution can be computed in closed form using the Bayes rule. So as I said, they just use cross entropy loss. They just noise, and then denoise. They learn the denoiser of that transformer in order to find the parameters of the denoiser. That's it. That's the idea. And whenever you see X is node features, whenever you see E is edge features. For example, in language modeling, if we have some tokens and we flip it, for example, in diffusion, language model, diffusion, LLM, you flip it. Here, we flip the nodes with node types. We flip the edge type. So, again, the simple idea. But the graph is different from language in the sense that it has topology. You cannot, if you add noise to that, of course, we modeled with categorical data, not Gaussian distribution. But if you add noise to that, it has a sparsity. The topology changes completely. So you need to also use some structural features like degree that they use in Digress. And the cross entropy of edges, the cross entropy of nodes. This is a hyperparameter to say which one. Of course, we use an advanced approach. This lambda adjusts itself, but you can write this probability, this distribution, as a product over nodes and edges. When you want to transition, when you want to do denoiser, denoiser also always has a parameter. But the forward is fixed. Here in this paper, they don't learn the forward. But I've seen many papers that they schedule the forward as well. Of course, if you do that, then you should think about how to write it to make it more explicit, and you can derive it explicitly for analysis, And this is the lemma that says digress is permutation equivariant. Another lemma says invariant loss. Another lemma is exchangeability. Digress yields exchangeable distributions. It generates graphs with node features and adjacency matrix. And this is the reverse diffusion chains. Start from a model trained on uniform transition noise. When noisy graphs have right marginals of node and edge types, they are closer to realistic graphs. So here they talk about the choice of that noise model. So they propose this hypothesis using a prior distribution, which is close to the true data distribution, makes training easier. So they propose this Q for both nodes and this for edges. Whenever you see M is marginal, here, for example, is the probability of jump. If you want to jump from state I to state J, for example, from carbon, it becomes hydrogen, then that is proportional to the marginal of category J. For example, the probability of hydrogen goes to carbon, let's say another state from nitrogen, what is the probability? Then you add them, so it becomes the marginal probability. This is in probability is a marginal distribution. You condition on something. You add them up. Of course, here is discrete data. This integral becomes summation over all nodes or over all edges. Edge type, node types. But this here Q. And for the same analogy, when you see Q bar, you should multiply all of these alpha that has, because you jump from 1t to the data. And beta is always, papers, they usually define 1 minus alpha. So you can easily convert them. And the training, as you see, is just you learn this denoiser. Of course, as I said, you use structural and spectral features. Like eigenvectors of Laplacian is good. There are other approaches like, I remember, relative random walk probability. This one. There are many approaches. You can use approaches Professor Bronstein in Oxford University. He used learning the kernels, those filters. There are approaches like anonymous random walks. There are many approaches to model structural information of the graph. Then you use this, and then you find the denoiser. You predict it using this cross-entropy loss of edges and nodes. But the sampling is different. You just, because you use forward, use structural features, here is the same. The forward pass, you need to know that because you want to just sample it. It's a sampling. Here we are not learning anything. We have already trained something, so we know the parameters of the denoiser. You just need to create it. So you go through t time steps in order to find one of the points either in distribution or out of distribution, but it should have good novelty, uniqueness. Of course, it should be valid. And they talk about conditional generation. So they use this sampling from Digress algorithm 3 with discrete regressor guidance. It has a guidance. So everything is the same. They just multiply this by this guidance distribution that they approximated as an exponential distribution, e to the minus lambda. And their work is related to many things. So, QM9, Zinc, Moses, these are important data sets you should know. The most important, there are many measures, but here for QM9, they just did validation and uniqueness. Nowadays, we have around 10 to 20 different measures to see the performance of your diffusion-based graph generation. And this is a stochastic block model, which is very important in pure mathematics. But nowadays, stochastic block model, you see it in machine learning everywhere. In social media, it has that kind of structure. Also Moses. These two, if you want to do good thing, you should go beyond QM9 and Zinc to 250K. These two also are fantastic. And you see FCD, for example, in computer vision, we use FID, Frecce inception distance. For graphs, we use uniqueness, novelty, KL divergence, validity, filters, SNN, scaffold, so many measures. They did it for Moses. And this is the mean absolute error on condition, because they have a conditional version of their generative model. They condition on homo. There are many variables you can do, but they did it on these. So you can compare them if you're conditional, unconditional, or with guidance. So in their appendix, they review these things. It's very important to read the appendix very carefully, just to review from first principles what is happening. If you want to develop new ideas, you need to have a good terminology, good theoretical background, and see all of these things. So in algorithm 4 and 5, now they sampling from Congress. They also talk about that. And then in appendix E, they say our model is permutation equivariant. It doesn't matter what entries are masked. We therefore choose the first n ones. After sampling, we update x and e. And experimental details, additional results. This is abstract graph generation. The metrics that they use, we do not draw reports, raw numbers, but ratios computed as So the MMD of generated and the test squared over MMD of training and test. So in the denominator is we have generated and test, and denominator training and test. So it means it's high if generated is the MMD is similar to the training and test of the generated and test is similar to that. And this is the architecture of the, you can use any graph transformer. This particular one is interesting because you can also add edges to that, not only node type but edge type, also the property, global features. So here is the set. It's about structural modeling of the graph, and therefore, of course, they did some. For example, they added some features like here you will see how they encoded the features. You can also add for optionally they can use spectral features as well. It's an option. You can use any method you like. We also incorporate the current valency of each atom. For example, carbon has valence of 4. It means that 4 atoms can be connected. For example, CC, 2 is, so we have 2 more, HH. I've learned some chemistry in order to appreciate these things. For example, N is 3, H is 1. So this looks like a stable molecule. It has low energy. In quantum chemistry, they do lots of very expensive things to understand these things. But with diffusion-based methods, we can, and graph neural networks, we can do many things so that we reduce the cost of computational quantum chemistry. And QM9 is one of those data sets that they used originally for quantum chemistry. So then they talked about this Moses. This is interesting. You can see the non-curated samples generated by Digress, trained on QM9 with implicit hydrogens. We don't show hydrogen because, there are many hydrogens. And so we have carbon, oxygen, hydrogen, nitrogen, fluoride. This one is 1. Nitrogen is 3. Valence of hydrogen 1. Oxygen, I think 2. Carbon is 4. Yeah, 2 is definitely 2. Like H2O, which is a stable. H2O.